Hey everyone, back to chapter 2 here. I hope you already have or you are going to shortly start doing some practice and doing significant figures calculations with them. Um, and I finished off this slide on last time, didn't get a chance to talk about it. But I do want to show you that this is not just a plot to torture freshman chemistry students. The accuracy of numbers matters a lot in different real-world applications. Move that down a little bit. For instance, machine shops. And I like to give this example. I used to work in a place that developed a lot of engineering drawings to send to a machine shop, so the engineers make them, and then the machine shop looks at them and decides if they can do it, how much it's going to cost. And the engineers would typically, this was purely based on laziness, they would prescribe the maximum tolerance on each of the cuts that they could get. And sometimes that was okay, but sometimes the machine shop would come back and say, you know, look, just because of the angles and, you know, specifics of the part, if you actually want this level of precision on the cut, you know, typically they would do like, you know, 1/1000th of an inch. You know, if you actually want this level, then it's going to cost you like $10,000 a part. You know, your call. And then the engineers would have to not be lazy and go back and calculate, you know, like, okay, how much do I actually need for this particular cut? So machine shops and engineering calculations definitely. Medication dosage, just to give you another one. The accuracy and the precision matters, which we're determining those values. All right, so a couple of real-world examples. A little bit on units of measurement. We're going to use several different units over and over again. Just want to kind of throw a couple of out there. Mole is a counting unit used in chemistry. Meter, length, gram, mass, liter is volume, Celsius, and time would be in seconds. So temperature will a lot of times be in Celsius or Kelvin. And then byte. All right, we're not going to use that too terribly much for this class. But you need to get used to dealing with units and attaching units to numbers. Most of the time that number absolutely must have a unit attached with it. And it follows it along as if it's an algebraic constant, which is going to be important for what we're going to talk about today, dimensional analysis. You're also going to have to deal with metric prefixes, and I'm sorry, you're just going to have to memorize some of these terms. So go to your book. Your slides for Ravel give you all of these. You need to know all of these. I've just, you know, reprinted a couple of them here. Deci, centi, milli, micro, nano, pico, femto, kilo. All right. And then, right, these are making them larger. These are making them smaller. You need to know how to use this. These are basically moving the decimal place around. Centi is, you know, basically splitting it up into 100. So a centigram is 100th of a gram. And then you need to know how to do conversions between centigram and grams. The way that we normally do that is by setting it up as an equivalence. We're going to talk about this more when we talk about dimensional analysis, but say you're talking about a centigram, you say 1 gram is equal to 100 centigrams. Okay. This then determines an equivalence that you can use. So if I put 1 gram over 100 centigrams, then that just equals 1. So I can multiply anything I want by 1, and it's not going to change the actual number. All right. This is the idea behind dimensional analysis, just multiplying by 1. And it's also the idea for how you're going to convert these. But you need to know these conversions to get from the common prefixes, you know, giga, mega, kilo, deci, centimilla, and the base units themselves. So you have to know what these are. And then another note for you. Make sure you're consistent. A lot of times if you Google it, you know, they'll show the number on different sides. So we could have written 1 centigram is equal to, you know, a gram divided by 100, right? Or 10 to the negative 2 grams. Make sure you're just consistent in how you use it, and you realize that those have just switched the 100 from different sides of the equation. All right, I'm going to move on. This is going to be dimensional analysis. I like to start off with something really, really easy. 12 inches is a foot. And you can see when we're converting between units, we just want to multiply by 1. So 12 inches divided by 1 foot is just 1, right? So we need an equivalence. 12 inches is equivalent to 1 foot. We put them as a fraction, and then we can convert between different units. This is the basic idea. I want you guys to get really used to this, because chemistry is basically just a bunch of conversion factors between different units. So for instance, if I had, say 36 inches and I wanted to convert that to feet, then I could multiply, and this is the trick, you got to make sure you put the inches on the proper side, right? Which of these am I actually going to use? Well, the one that includes inches on the denominator. So 1 foot is equal to 12 inches. And then you see that inches cancels out. Okay, if you use the wrong one, then you're going to get some funky units at the end. It would be inches squared per foot. Not correct. So if I wanted to say, hey, I have 36 feet, how many inches is that? Then you need to make sure you use the other one where foot's on the bottom. So 12 inches is equivalent to 1 foot. And then you see that feet cancels out, and you're left with 36 times 12, whatever that is. Okay. Another easy example I like to give students, just to kind of lead up to this. This is not just length and length. Is something like speed. So you're kind of used to something like this. So let's say I wanted to drive to San Antonio. San Antonio is about, let's say 400 miles. I don't know exactly what it is. And I want to figure out approximately how long is it going to take me to drive that 400 miles. Well, this is just a conversion factor where I'm going to say 400 miles is going to turn into how much time given some average speed. So let's say I'm meticulously drive only 60 miles an hour, then my conversion factor is 60 miles is equal to 1 hour. That's one way of thinking about it. We're totally used to, for these, just doing miles per hour. So that would be 60 miles over 1 hour is my conversion factor. But you can see the way we normally write it is not the way we want it. All right. In this case, miles is on top, and it's not going to cancel out. And so what you do in this case, just like we did for the units over here with distance, is you just flip that over. Okay. So let me go ahead and get rid of all of that. We're going to flip it over, and we're going to say 1 hour is equivalent to 60 miles. When I write it this way, then my distance units cancel, and I get time coming out in hours, and that's what I wanted. So this is going to take us, I don't know, 4.5 hours, something like that, whatever it is. We could do the same thing if we said, hey, I'm going to drive for 3 hours. How far can I drive in that time if I'm on average doing 60 miles an hour? In this case, we can write the units like we're used to. Right? 60 miles is equivalent to 1 hour, and then the time units cancel, and I get, 180 miles, right? Okay. In order to do this, you must make sure to write your units, all right? So get used to that. Also, there's something interesting here, is that the units themselves are telling you that you set the problem up correctly. Dimensional analysis is your friend. It tells you if you set the problem up correctly because the units work out. It also can sometimes give you a hint in how to solve a problem. Let's say you're not sure how to, calculate, well, I'm driving for 3 hours. How far am I going to get? I'm not sure how to do that. Well, you think about it, oh, just use it as a conversion factor and make sure the units cancel. So that would mean I have to set it up with miles per hour. All right. Excuse me. All right. So a couple of simple examples for you, and that's fine. All right. You know, maybe you haven't seen this type of stuff before. Hopefully you have, and you'll just jump right into it. But if not, remember, should get a little bit extra practice so you are. Okay. Dimensional analysis implies using dimensions to help solve problems or make sure no mistakes were made. That's what I was talking about. This is used in various industries and applications. You can use it for more complicated combined units like energy, which has units kilogram meter squared per second squared. And then you can use it for, you know, say your pay. You know, you get paid $8 an hour. I'm sure you guys are all well familiar with that, figuring out if I work 5 hours, how much money am I going to get? All right, we can draw different examples, but I think I'm going to leave it at that and let you get your practice in the homework. Okay. Converting between different prefix units works the exact same way. Make sure you get used to these, and also there's a little bit of memorization for you. You need to memorize these different ones. So let's say we want to do 3.55 kilograms to grams. Well, the conversion factor is kilogram is equal to 1,000 grams. Okay, so this determines my conversion, and I can just set it up, you know, one on top or the other depending on which direction I'm going. In this case, we want to go from kilograms to grams. Forgive my handwriting there. So I'm going to use the one where it's 1,000 grams over kilograms, or 1,000 grams is equivalent to 1 kilogram. Then kilograms cancels, and I just get 3.55 times 1,000, which will give me, again, I don't want to put zeros on there. It's going to give me a different set of significant figures. So I'm going to go ahead and just write it in scientific notation. Squeeze it all on there. That would be 10 to the third power, and that is all in grams. Okay, hopefully that's all legible for you. I'll let you work these other guys on your own. You need to go look up the actual conversion factors, and then you can get those answers. Derived units are just something that takes some of the base units and builds on them. It could be something as simple as volume, in which case it's just going to be 3-dimensional units put together, right? So instead of centimeters, it'd be centimeters cubed. All right. Converting units, so pressure is one of those ones that we'll use a lot later, and I'll normally give you most of these conversion factors, except for the prefixes. You need to get those. But something like torr in atmospheres, 1 atmosphere is 760 torr. That becomes your conversion factor. This is your equivalence that you're using. So if you're given 587 torr, then you would just use this. And the way you want to set it up is, you know, 587 torr. And so you need the one where it's atmospheres on top, divided by 760. Okay. So torrs cancels, and you get whatever that turns out to be. And the only units you have left are the atmospheres right there. Okay. They spend a significant portion of time talking about temperature and temperature conversion factors in the book. And that's great. I would like for you to go look up those conversion factors. Here they are, right? And then get some practice doing these temperature conversion factors. To go from Celsius to Kelvin is the easiest one. All right, you just need to add 273. To go between Fahrenheit and Celsius, is fairly simple. You just need to make sure you get the order of operations correct. A little bit of memorization, sorry, a little bit of just figuring out the order based on the formula. Again, most of the time I'll give you the formula. But I'd like you to go look at that. Also, you'll see they have a nice handy picture that tells you exactly how they're related. So Fahrenheit and Celsius, you can see Celsius goes from 0 to 100 for freezing to boiling point of water. Whereas that same distance, right, it's the same temperature increase, but for Fahrenheit, it goes from 32 to 212. So the Fahrenheit degree is a little bit smaller, right? It's about half the size. And you can see they're also shifted a little bit. So they're not at the same 0 scale. 0 Celsius is not equal to 0 Fahrenheit. So check that out in the book. Again, I don't want to go over every single little detail, leaving some of that for you guys. Okay, let's talk a little bit about accuracy versus precision. And this is a discussion that's pretty easy to get. And the typical example I'm going to use, the typical one, is to think about it in terms of shooting at a target. So let's say you have a target and you got the bullseye in there, and you go and you shoot your bow and arrow or whatever it is, and you get hits that are kind of all like that. Well, you look at it and you say, hey, my sights must be off. All right. And this is actually not such a bad situation to be in. You're having your sights off because you can correct your sights, and at least you're getting a consistent, what we call, grouping in there. This would be called precision. All right, is how close together the values are to each other. And in science as well, we can say this is not actually that bad of a thing. I can correct for it. So if I had a thermometer that always gave me, +3 degrees, that'd be okay. All right. If I have my bullseye or my target here, and I got values that were, like just kind of all over the place, then I could say, well, I kind of have an accurate thing on average, right? And this is kind of a difficult position to be in. I don't have precision for these. They're not agreeing with each other, but on average, they're accurate. This is probably the worst thing that we can get when we're looking at something. And in this case, you kind of can say you have an accurate measure because on average it gives you the correct one, but it's not precise, and so it's sort of difficult to make out exactly what's going on. So this would be kind of a situation where you have accurate but not precise. The previous one we had precise but not accurate. And then you could have a situation where, whoopsie, you have your target. I'm getting in a hurry here, and you are just all over the place, and they're not close, and they're not on average giving you the actual target or the bullseye. And this is the worst of everything, right? We're not accurate, we're not precise. This would be the worst situation that we can give. Now we're talking about measurements for an instrument, right? We're not talking about bullseye, but we get these same factors that come up when we're talking about instruments. All right. So dimensional analysis is your friend. Make sure you get some practice with it, and here's some helpful hints. Always write your units. All right, and then your units are just canceling as if they were algebraic constants. So if you have your units in there, then you can cancel them out or make sure they cancel as algebraic constants. If you don't even write them in there, which to be honest is a common thing I see, and it's usually on people that get the problem wrong. They didn't have that there to help them in some sense. Maybe it could have helped them get the question. And then set your problem up. This is a good thing to think about. Write down every single thing that's listed in the problem. This is general problem solving tip. Write down everything with the units, and then your units can kind of be used to see exactly how do I get from there to there. Okay. The last one we're going to talk about, I'm not going to spend much time on it, is on density. Right? You need to know about this. This is, again, just another conversion factor. In this case, the conversion factor goes between mass and volume. So the normal units that we're going to use for density are grams per milliliter. And then, if you're given mass, then you can convert to volume using your conversion factor or the density for that substance. If you're given volume, then you can determine the mass, just making sure that you have the correct configuration of your density. So if it's 5 grams per milliliter, maybe you need the 5 grams on top, maybe you need it on the bottom. And remember, the way it's written usually is, that number is kind of attached to one or the other on the numerator. So if I need to switch it, then it would be 1 milliliter is equivalent to 5 grams. So that 5 follows the grams around. So here's a practice problem for you. Make sure that you can convert the gold, right, which has this density, or you can calculate the density, and then we have a follow-on. Oh, I don't have the follow-on here, sorry. So you just need to determine the density here, and remember, you're going to use the correct number of sig figs in these calculations, because you're always going to use sig figs in the proper operations for the rest of the semester. And this is just an interesting little example. Found this on the old textbook we used to do by a guy named Tro. In 1999, NASA lost almost $100 million orbiter because 2 groups of engineers failed to communicate with each other on the units they were using for the calculations. All right, this disaster had a big effect on the way NASA does business, and you still had a fight between the people that wanted to use metric and stick with the normal units, but you have to be consistent in your units, and it's important. All right, another interesting application for you. My wife figured this out. The kids' version of medicines, so like say children's Tylenol, are usually like twice as expensive as the adult ones. And when you look at the units, you find out that you could get the same amount if you just got the adult one for half the price, right? And just gave them, one of the pills. It's kind of a little trick they do, and I understand the reason, right? Some kids need less, but most of the time, your kid gets to be 8 or so. You could just give them 1 pill, and it'd be the same as the way more expensive children's dosage. So just another example of real life application of dimensional analysis in this case. So get some practice, work problems. Just wave my finger at you on the one, and y'all have a good one.